Welcome again to our series of lecture videos in Module 1. This lesson looks at pH changes in acid-base titrations as well as ionization constants of acids in solution. Now, we've been looking at, particularly in the last lecture, at the strengths of acids and bases in solution and the effect of their ionizations in water in determining the strength of acids and bases. In this lecture, we're going to explore some different kinds of acids and bases and how it is that they interact with each other, or react with each other, and effectively look at the changes in pH and what the changes in pH can tell us about the concentration of H3O plus in solution, as well as how it is that we can actually use those values to determine unknown concentrations of solutions. And then we want to look at some kinds of acids, particularly polyprotic acids, that have a different kind of ionization, and use the ionization constants to be able to determine the concentrations of these ions in solution. Here we have a picture of a pH meter, one that is used in many acid-base titrations, and a typical acid-base titration involves adding an alkali to a burette and determining the pH over the progress of the reaction, and at neutralization point determine the volume of reactants, and ultimately one can calculate the concentration of an unknown solution. Now, this is this kind of experiment is one that you're going to be doing in the CHEM 1065 laboratory course, particularly determining the concentration of I think vinegar in solution, something like that. So let us look at an example of a titration involving a strong base and a strong acid. Let us consider the reaction between 20 centimeter cube of a 0.1 mole per dm cube HCl solution and 0.1 mole dm cube aqueous sodium hydroxide. In the titration, controlled amounts of the sodium hydroxide solution are added from the burette to the solution of the acid in a conical flask. Here we have the reaction involving the HCl and the sodium hydroxide to give us our salt and water. It's very familiar to us. And here we have the neutralization sequence, essentially involving H3O plus, which would have been formed in our HCl solution, and OH minus, which would have been formed in our sodium hydroxide solution, both reacting to give us H2O. This is supposed to be 2H2O, by the way. So what we want to do, or to explore, is to answer these questions. One, how does the pH of the solution change during the titration before neutralization? And how does the pH of the solution change after neutralization? Certainly before we actually are able to determine what happens during the course of the reaction, or at neutralization or after neutralization, we have to know what the pH of the solution is before titration. Now, so when we started out our reaction, we had our beaker or solution made up of hydrochloric acid. What essentially is happening there? We have HCl added to water, and because HCl is a strong acid, we expect that there is complete dissociation into our chloride anions and our H3O plus cations. And because of the 1-to-1 mole ratio of HCl to H3O plus, we expect that because HCl, all of the HCl is diminished, and there's maximum formation of H3O plus, then the concentration of H3O plus is equivalent to the concentration of the starting HCl solution, which is 0.100 mole per dm cube. Now, because we have the concentration of H3O plus, we can then calculate the concentration of, the pH of the solution before the reaction, and that turns out to be equal to 1.00. Now, so during the titration, we are adding various amounts of sodium hydroxide, and essentially what is happening is that the concentration of the H3O plus is diminishing or decreasing. And at neutralization, we have 20 centimeter cube of the sodium hydroxide used. That's basically what the question told us, or the case told us. You can recognize that it had to be 20 centimeter cube of sodium hydroxide because, one, the molar ratio, or the mole ratio of the sodium hydroxide to HCl is 1:1, and also the concentration of the sodium hydroxide and hydrochloric acid are equivalent. And so therefore, at neutralization, where we have all of the H3O plus reacting with the 20 mils of OH minus, we have the formation of 2 moles of water. And so we can therefore say that the concentration of H3O plus is equivalent to the concentration of OH minus. Now, what is the pH at this point of neutralization? We're saying here that the concentration of H3O plus is equal to the concentration of OH minus. Now, if we go back up here and look at this equation, this gives us a reminder of the ionization, the self-ionization of water. Remember, you have, in a solution of water, you have some molecules acting as acids and some acting as bases, and therefore you will have the formation of hydroxide anions and H3O plus anions, which tells us that we can use the self-ionization constant Kw to help us to calculate the concentration of H3O plus in solution. And so we know that Kw is equal to H3O plus H3O plus, the concentration of H3O plus times the concentration of OH minus. And since the concentration of OH minus is equal to the concentration of H3O plus, then we can actually substitute that concentration into our Kw, which is equal to H3O plus squared, which is equal to 1 times 10 to the minus 4 mole squared dm to the minus 6. That's something that we should know. And then we can square root this function to get 1 times 10 to the minus 7 mole per dm cube, and then the pH is equal to, as calculated, to be equal to 7.00, which effectively is the point of neutralization, the point at which all of the H3O plus from the acid reacts with the 20 mils of hydroxide that is added in the reaction. And we call this point as well the neutralization point, but we call this point the equivalence point, the point at which the number of moles of the acid is equal to the number of moles of the base, or the number of moles of the H3O plus is equal to the number of moles of the OH minus. So how does the pH of the solution change during the titration before the neutralization? Well, at the start or before the start of the reaction, as we had pointed out earlier, we have our solution of HCl in water, right? And we have complete neutralization into our Cl minus and our H3O plus. Now, as sodium hydroxide is added, we have the H3O plus concentration decreasing or diminishing because the hydroxide ions are reacting with it, are using it up to form H2O. And because the concentration of H3O plus is decreasing, the pH is rising. And so, what is the pH of at that point? We have to determine what the concentration of H3O plus is. We have to go back to the 1:1 mole ratio, HCl to NaOH, to give us our sodium chloride and our water. And based on that 1:1 mole ratio, we're able then to calculate what the concentration of H3O plus is, which essentially is equal to the moles of HCl at the start minus the moles of sodium hydroxide added over the total volume of our reaction mixture. And so our HCl, in order our H3O plus, in order to find the moles of the acid and the base, we have to multiply the volume of the acid times the concentration, and the volume of the base times the sodium hydroxide. And so the concentration of the H3O plus is equal to the moles of the acid minus the moles of the base over the volume, total volume, which turns out to be as shown here. Now notice that we are using dm cube. We are converting from centimeter cube to dm cube effectively. So inserting our values and doing our simple math, we end up with the concentration of H3O plus being equal to 0.0200 minus 0.10 Y over 0.02 plus Y. Note that Y is the volume of base added, whatever that volume is. And so we can easily find the pH, which is minus log to the base 10 of the H3O plus concentration of H3O plus. So here we have a table showing the volumes added over the series of the progress of the reaction, and we have converted from centimeter cube to dm cube. Recognize that 1 dm cube is equal to 1000 centimeter cube, so therefore if we are converting from centimeter cube to dm cube, we have to divide by 1000. And these are the equivalent pHs. When we have 10 centimeter cube, we have a pH of 1.4. When we have 19, we have 2.5, 19.9, we have 3.6, and 19.99, we have 4.6. So how does the pH of the solution, I'm not sure if I'm supposed to get there. Yes, I am supposed to. So now that we've determined what the pH of the solution is at the start, what the pH is at neutralization, and what the pH is from the start up to neutralization, then we need to find out how does the pH of the solution change after neutralization. Remember that at neutralization we have the concentration of H3O plus equaling the concentration of OH minus. That is to say that all of the OH minus ions have used up all of the H3O plus ions. And so if we continue to add hydroxide ions, then we're going to have an excess of hydroxide ions in solution. And so how do we calculate the pH? Well, we know that if we have the pOH, we can use the equation pH plus pOH, which is equal to 14, to determine what the pH is. And so if we add another or another centimeter cube of base to the solution, that is to say we've now added a total of 21 centimeter cube of sodium hydroxide, then we have a total volume of 41 centimeter cube in our reaction mixture. And so what is the concentration of OH minus? The concentration of OH minus is equal to the concentration times the volume over the total volume. And that is going to be equal to 2.44 times 10 to the minus 3 mole per dm cube. And so the pOH is equal to 2.6, and therefore the pH plus pOH being equal to 14 allows us to be able to calculate the pH, which is equal to 14 minus 2.6, which gives us 11.4. So clearly we can see that with the addition of a small volume of OH minus, the pH changes drastically from 7 at neutralization up to 11.4. And what we're going to do is to plot a graph which is called a titration curve of pH versus volume of base added. And this is the shape that is typical for strong acid, strong base titration. So here we see over here that we're adding the volume of sodium hydroxide from 0, we could add 1 and 2 and 3 and 4 mils and so on, up to 10. We see that the pH changes very slowly, and then it starts to change more significantly up to 19 and 19.9, and even more drastically between 19.9 and 19.9 and 20. 0.01 mil, or rather 0.1 mil, changes the pH by 3 point odd, because we're moving from 3.6 to 7.0. And then when we add another mil, we're going all the way up to 11.41. And so a plot of the pH versus volume gives us this curve where there is a steady increase of the pH, and when we get close to neutralization, there's an inflection, and then there's a sharp change at neutralization. Thereafter, on addition of excess base, we have the pH increasing steadily. Now at this point here is called the equivalence point, and for a strong acid strong base titration reaction, it occurs at a pH of 7. Now if, for example, we were doing this reaction and we didn't know the volume of sodium hydroxide that we were adding, then we could determine easily by interpolating along the x-axis the volume of base added And then from the volume of base added and the mole ratio, we can actually work back to find out what the concentration of our sodium hydroxide is. Now, this set of titration curves show differences with respect to concentrations of both our HCl and our sodium hydroxide. And let us highlight some interesting things that appear. What we find is that the lower the concentration of our solutions, the higher is the starting pH. So in this case, where we have the HCl and the sodium hydroxide being 1,000 times smaller than what it was at 0.1, then we see that the pH at the start of the reaction is higher, right? So if you look at 0.02, it is higher than that for 0.01. And what that's telling us is that if we have a lower concentration of acid to start out with, it means that we have, even though we have complete ionization, we still have a smaller concentration of H3O plus in our solution, and therefore the pH will turn out to be higher. And so, but the curve obviously remains the same, with irrespective of the concentration of solutions that you're using. You still end up with the equivalence point occurring at a pH of 7, but the narrowness of that equivalence point area is smaller. Again, you can still interpolate to determine what the volume is, and then calculate the concentration of our solutions respectively. Now, what happens in a case with a weak acid, strong base? We can use an example of a weak acid. We can use ethanoic acid, and a strong base we could still use sodium hydroxide. If you notice that the shape of the curve is more or less the same, there are some slight differences, of course, or some distinct differences, I should say. One is that the pH before the equivalence point is generally higher than in the case of the strong acid, strong base. And this is because if we think of the equilibrium reaction of the ethanoic acid with water to form our ethanoate anions and our H3O+, the equilibrium, the ethanoic acid actually does not ionize fully to give us any appreciable amount of CH3CO2-, and therefore the concentration of CH3CO2 is much less than in the case of a strong acid, and therefore the pH is going to be much higher. The trend up to equivalence point is more or less the same, but the second thing that is different between a strong acid, strong base reaction is that the equivalence point is much greater, is in fact greater than 7. In this case, it's about 9. And the reason for that is that the ethanoate anions that are formed on ionization of the ethanoic acid, in fact, react with H2O to form back our CH3CO2, note at neutralization still, but that allows for an excess of OH- ions, and the excess of OH- ions effectively increases the pH of our weak acid strong base reaction as compared to that of a strong acid strong base. Here is another example of a titration curve of a strong acid and weak base. What I want you to do is to look at this titration curve, and in your textbook or other textbooks, read and understand why it is that the shape of the curve is opposite to what we have seen for the weak acid, strong base, strong acid, strong base reactions. Now, so we're going to turn our attention now to look at the second part of our lecture, and that is monoprotic and polyprotic acids. Now, monoprotic or monobasic acid, as they are described as, are molecules that have one ionizable proton. And we're familiar with those. For example, HCl, nitric acid, ethanoic acid, benzoic acid, and so on are examples of monoprotic acids. They have only one proton to ionize in water. So here's a typical equilibrium that we're familiar with. However, the polyprotic or the polybasic acids are those whose molecules have more than one ionizable proton in the molecule. And examples of that are sulfuric acid, phosphoric acid, carbonic acid. Here we have 2, 3, and 2 ionizable protons in the molecules. And the difference in the equilibria between monoprotic and polyprotic acids is that in polyprotic acids there are more than one ionization reactions. And so in a typical case, for example, in a diprotic case, where you have H2A plus H2O giving us HA minus plus H3O plus, this is the first ionization step, and hence the ionization constant is Ka1. This conjugate base that is formed now acts as an acid in the second ionization step to react with water acting as a base to give us a different conjugate base and additional H3O plus. This table here is showing us the ionization constants of several polyprotic acids based on the different ionization steps that are involved. Let us look at the first one. Hydrosulfuric acid is H2S. It's a diprotic acid. In water, it gives us H3O plus plus HS minus, and the associated equilibrium constant is 1 times 10 to the minus 7, and the pKa is 7.0. This HS, which is a conjugate base, now acts as a conjugate acid to donate its protons to our H2O in a second ionization step to give us H3O plus and S2 minus. And the corresponding ionization constant is 7 times the order smaller than the first ionization, and the pKa is several times larger than the pKa1. Let's jump down to sulfuric acid, which we're familiar with. We have H2SO4 plus H2O to give us H3O plus and our conjugate base HSO4 minus. This conjugate base, before we say that, the Ka which is the Ka1, which is the first ionization constant, is extremely large. In fact, in many cases it's 10 to the 3, order of 10 to the 3, and the pKa is much less than 0, and the conjugate base that is formed now acts as a conjugate acid because it's donating a proton to the water to give us H3O plus and another conjugate base, and we can see that the Ka for that ionization step is much smaller than Ka1. So and the thing about it is that when we look at all of the examples, we see that the first ionization Ka or Ka1 is much larger than Ka2, right? Ka1 larger than Ka2, Ka1 larger than Ka2, and so on and so on. In fact, in most cases, in all cases, Ka1 is several times the order larger than Ka2. And so the question is, why are the second ionization constants considerably smaller than the first? And also, what does that tell us about the formation of ions in solution? Here we have another table showing us examples of polyprotic acids and highlighting to us the ionizable protons and the corresponding Kas for the 2 steps or the several steps that there are. In this case, arsenic acid has 3 ionizable protons, and we have 3 Kas. We're moving from 6 times 10 to the minus 3 to 1 times 10 to the minus 7 and 3 times 10 to the minus 12. If you look at this, let's just back up to look at the other table. In this table here, we're showing that the ionization constants in fact are getting larger as we're going down the table, which is telling us that our acid strength is increasing. So we could probably from looking at the change in ionization constant, getting some idea as to what is happening between the first ionization and the second ionization, based on the ionization constants that we see for each acid. Alright, so let us explore that by looking at the ionization constants of phosphoric acid, which is H3PO4. For phosphoric acid, we have 3 ionizable protons, and therefore one can expect that in solution there are going to be 3 ionization steps. The first one is H3PO4 plus water to give us H3O plus H2PO4 minus. We have Ka1, the corresponding constant is Ka1, and then we have the H2PO4 that is formed in the first step, reacting with water to give us H3O plus and HPO4 2 minus, and the corresponding constant is Ka2. And then the HPO4 2 minus that is formed reacts with more water to give us H3O plus PO4 3 minus. Now, when we look at the corresponding ionization constants, we see that we are moving from Ka1, which is 7.1 times 10 to the minus 3 mole per dm cube, to Ka2, which is 6.3 times 10 to the minus 8 mole per dm cube, to Ka3, which is 4.2 times 10 to the minus 3 mole per dm cube. Of course, we can determine the equilibrium constants, or the dissociation constants, or the ionization constants, from our equilibrium reactions. And so the question is, what is the explanation for the magnitudes of the ionization constants? Why is it that Ka1 is several orders times greater than Ka2, and even many, many more orders times greater than Ka3? Well, before I move on from there, the point is that if we go back to the equilibrium reactions. If we look at this reaction, the first one, we can essentially say that the hydrogen that is lost from the H3PO4, the H plus, the proton that is lost, would have been interacting with an anion that is -1, and that is not an energetically difficult process, and so Ka1 can be fairly appreciable. But if we look at the second ionization process, then the proton that would have been in H2PO4, you can consider it as being attracted to an HPO4 anion that has a 2 minus charge. And so the pull on this from this HPO4 2 minus on the proton is going to be much larger, and therefore it's going to be much more difficult for the for the proton to be lost from this HPO4 minus. And even further, when we look at this one here, we can consider another proton interacting with a PO4 3 minus anion, a much stronger pull, electrostatic pull, on that one single proton, and it's a much more difficult separation than in the second step and than in the first step. And so that is essentially simply the reason why it is that Ka1 is greater than Ka2 than Ka3, because the formation of the corresponding anions as we go down the steps of the ionizations becomes more challenging, and so the equilibrium constants are less likely to be directed to the right, but more likely to be directed to the left, essentially. Alright, so what do the ionization constants really say about the ionization of H3PO4? Let us look at the ionization constants. We see that Ka1 is so much larger than Ka2 and Ka3, and this tells us that essentially all of the H3O plus is produced in the first step. Alright, so 10 to the minus 3 is several orders smaller than 10 to the minus 8 and 10 to the minus 13. It tells us that if we are going to determine the concentration of H3O plus in the solution, most of it is formed in the first step. Now, since, and also, and let's clarify that quickly. And also the concentration of H2PO4 is equivalent to the concentration of H3O+. Now, because if we look at now Ka2 tells us that the equilibrium constant is 6.3 times 10 to the minus h, which is again several orders times smaller than that of the of Ka1, and that tells us that the H2PO4 that is formed in the first step, yes, will likely react with H2O+, but not to a great degree to form H3O+. And HPO4 2-, and that tells us again that the majority of H3O+ that is formed again comes from our first reaction. There is a very small amount that is formed in this step, because if you look at the equilibrium constant again, it's so small that it's almost negligible in a sense, and it tells us that the backward reaction is probably more favorable if you were to influence equilibrium in that direction. And so, since so little of the H2PO4 from the first step ionizes any further, we can assume that the H2PO4 minus concentration is equivalent to that of the concentration of H3O+ in solution. Alright? And furthermore, if you look at Ka3, it's 4.2 times 10 to the minus 13, even significantly smaller than that of Ka2. That tells us that any amount of HPO4 2- that is formed is unlikely to react with any more water to give us H3O4 plus PO4 3-. And so, if we consider the equilibrium constant Ka2, right, because the concentration of H3O+ is equivalent to the concentration of H2PO4, then if we were to consider Ka2, right, then the concentration of HPO4 2- is equal to that of Ka2, because the concentrations of H3O+ and this H2PO4 are equivalent. And so, regardless of the molarity of the acid, the concentration of HPO4 2- is almost equivalent to Ka2 in our reaction. Let us look at sulfuric acid. Here we have H2SO4 plus water to give us H3O plus HSO4. This conjugate base reacts with more water to give H3O plus SO4 2-. The corresponding equilibrium constants are 1 times 10 to the 3 mole per dm cube and 0.01 mole per dm cube, telling us that the ionization is almost complete in the first step. That is to say that most of the H3O+ that is formed in the reaction is from the first step, and also that the HSO4 that is formed from the first step is not depleted by the second step, because the Ka2 for the second step is significantly, in fact, 5 times less than that of the order of Ka1. So let us explore this concept by looking at this question. For a 3 molar H3PO4 solution, calculate A, the concentration of H3O+, B, the concentration of HPO4-, C, the concentration of HPO4 2-, and D, the concentration of PO4 3-. Now, again, we need to apply some kind of strategy. What we should start out with is writing out all of the different ionization steps and the equivalent equilibrium constants for each step, right? And so for the first step, we have H3PO4 plus H2O to give us H3O plus H2PO4. Now, having done that for each step, what we should do is to determine or to write down the initial concentration of the species, then to determine what the changes or the changes that occur in the equilibrium or the ionization processes are, and then to find out what the concentration is after the ionization step has been undergone. So in the first step here, we have H3O PO4 plus H2O giving us these ions here. And so the initial concentration is 3 molar for H3PO4. Of course, for water it's constant, and at the start of the reaction, obviously, or before the start of the reaction, there is no H3O plus formed and no H2PO4. But once you have the addition of the H3PO4, there is going to be some change in the concentration of H3PO4, and we give that a value x, and because it's diminished, we say minus x, and because of the 1-to-1 mole ratio, right, the same moles that would have been lost from our H3PO4 is equivalent to the same moles that would have been gained for our H3O plus and our H2PO4. Now, what is the concentration after the process has occurred, or the step has been completed? That is essentially equal to the difference between the initial and what has changed. And so after the first step, the concentration of H3PO4 is equal to 3 minus x molar, and for H3O plus is x, and H2PO4 is x. Now, because H3PO4 is not a strong acid, right, we can assume that you don't have complete ionization, and therefore we can assume that x, which is the moles of H3O plus that is formed, or PO4 that is formed, is much less, significantly less than the initial concentration H3PO4. And therefore, if that is the case, then then 3.0 minus x is approximately equal to 3. And therefore, if we were to now plug in our values, right, in our equilibrium constant, which is Ka1, which is the product of H3O plus times the product of H2PO4 minus over the product of the concentration of H3PO4, which is equal to 7.1 times 10 to the minus 3 mole per dm cube, then we can essentially find x from there. Alright, and so x is equal to the concentration of H3O plus, which is equal to 0.14 mole per dm cube, which is also equal to the concentration of H2PO4. So, for part B, the concentration of H2PO4 is equal to the concentration of H3O plus, which is equal to 0.14 moles per dm cube. Now, for part C, where we need to find the concentration of HPO4 2 minus, we do the similar, apply the similar strategy as we did in 1, or for part A. We write out the equation, and then we determine the concentrations of the moles at the start, based on the changes that have occurred, and at the end of the step. And so we know that from the parts A and B that H2PO4 concentration is equal to 0.14 moles per dm cube. Water is constant. H3O plus is equal to 0.14 molar. Of course, at the start of that step, HPO4 2 minus is 0. Then the changes that occur, we are going to say that it's Y. So we have minus Y molar, or Y moles ionizing to give us Y moles of H3O plus and Y moles of HPO4 2 minus. After the step, what is left is 0.14 minus Y moles, 0.14 plus Y, and Ym. And so if we were to now use our equilibrium constant, which is H3O plus, the concentration of H3O plus times the concentration of HPO4 2 minus over H2PO4 minus, then we can plug in our values, and we get Ka is equal to, as shown here, we rearrange our equation and do our simple math. It turns out that Y is equal to the concentration of HPO4 2 minus, which is equal to 6.3 times 10 to the minus 8 mole per dm cube, which essentially is equal to Ka2, which goes back to what we had the case when we looked at H3PO4. We said that the concentration of HPO4 2 minus is equal to Ka2. The reason why is because if we assume that the concentration of H2PO4 minus is equal to the concentration of H3O plus, then these two values cancel, and the concentration of HPO42 minus is equal to Ka2, which is equal to 6.3 times 10 to the minus 8 mole per dm cube. What about the concentration of PO4 3 minus? Again, we write out the equilibrium, and we say that Ka3 is equal to the concentration of H3O plus times the concentration of PO4 3 minus over the concentration of HPO4 2 minus, which is equal to 4.2 times 10 to the minus 13 mole per dm cube. Now, we know that the concentration of HO plus is equal to 0.14. This is from the previous calculations, and also from part C, the concentration of HPO4 2 minus is equal to 6.3 times 10 to the minus 8 molar. And therefore, if we insert our values, it turns out that the concentration of PO4 3 minus is equal to 1.9 times 10 to the minus 19 moles per dm cube. Again, look at that, it's extremely small. And so, in our solution of, when we make up our solution of phosphoric acid in water, we will have ionization of the H3PO4 to give us H3O plus and H2PO4 minus, and there are going to be subsequent ionizations of those ions to give us other ions, but the predominant ions in solution are H3O plus plus H2PO4 minus, but those are considerably less than the concentration of H3PO4. So in a solution of H3PO4, we have majority H3PO4, some H3O plus, and some H2PO4 minus, as well as a very, very tiny amount of HPO42 minus and even less PO4 3 minus ions. So let us wrap up what we've learned from this lecture. We basically looked at some acid-base reactions in solution, which effectively done through titrations or titrimetry, and we monitor the pH change in those acid-base titrations, and use the pH changes to be able to allow us to calculate the determine the equivalence point, and also to calculate the amounts of unknown in a solution. Now we see that the titration curves change dependent on the strength of the acid and base, and it really has to do with the extent of the ionization that occurs based on the strength of the acid or the strength of the base, and the pH that those, for example, the acids would have at the start of the reaction and throughout the reaction. We've seen where polyprotic acids in aqueous solutions have more than one ionizable proton, and these acids undergo, as opposed to our monoprotic acids, stepwise ionization with different ionization constants. And we can use these ionization constants to effectively calculate the concentrations of various ions in solution, and that is particularly useful when we're looking at the strengths of acids in solution. So for the next session, we want you to continue to explore the concept. We want you to look at box 6.6, which looks at cooking with acids and bases, and then we want you to delve into looking at multi-step ionization of these polyprotic acids. An example here is malonic acid. We want you to look at or to calculate the concentration of the various ions in solution when you make up a solution of malonic acid in water. Further practice can be gotten from concept review question 7, and then in preparation for the next lecture, where we'll look at the impact of molecular structure on the acidity and basicity of various acids and bases, which can be seen in topics 6.6, 7, and 8. Alright, so see you at our next class. Take care.